adaptive model following system, state variable definition.
Well, I'm assuming that in the mask of Professor Skormin, I look much better and much more credible, and therefore we will continue discussion of the adaptive model following system in state variable definition. Last time I showed you how to build a linear model following system. You were supposed to realize that if we have a controlled plant that generally speaking may have all possible faults, including instability, including cross-coupling, and basically its properties could be absolutely unacceptable. What we can do, first of all, is to stabilize this controlled plant, making sure that at least it is stable. And after this is done, we can take a look at the design specifications. We can build a reference model, and we can enforce properties of the reference model on this controlled plant by building a linear model following system. Linear model following system is not an adaptive system. For linear model following system, we must know properties of the controlled plant. Now, if we have incomplete information about the controlled plant, then all our attempts to build a linear model following system will fail. And there is a place in the linear model following system where we can find the discrepancy between the controlled plant as operated by its local controller and the reference model. These discrepancies, this error, will not be equal to 0. And now we should make our next step. We should convert this error into, or built on the basis of this error, we can build a special adaptation mechanism that would force the control system, stabilized control plant with its state variable feedback, to behave exactly as the reference model. So our approach implies that number one, we design a linear model following control system. And then we perform step number two. We have to convert it into an adaptive model following control system by introducing an adaptation mechanism. And this adaptation mechanism will utilize the state generalized error, the discrepancy between the control plant with its state variable controller and the reference model. So let's take a look at the definition of our problem. First of all, we have this reference model, and in this reference model state vector is x. This is fundamental matrix of the reference model, A model, state vector x. This is matrix B of the model, and the reference signal R. That could be a vector, of course. Now, this information is perfectly known to us because the reference model is built on the basis of the design specifications. And here we have the controlled plant. The state vector of the controlled plant is y. This is derivative of the state vector of the plant. For the controlled plant, we have matrix, fundamental matrix AP times state vector. We have matrix BP, P stands for plant, and we have U. U is the control effort. That is, generally speaking, is not equal to the reference. Now, we have to define the control law. And what you can see here, the control law is defined as state variable feedback controller. This is the part that comes from the reference model. This is matrix Km times the state vector of the reference model. And this is matrix Ku times the reference signal. However, since we built an adaptive system, I want you to see that state variable controller matrix Kp is time and error dependent. And matrix Ku, since we're building an adaptive system, is not fixed. It is error and time dependent. Now we should introduce the adaptation mechanism. This is time-dependent matrix Kp, the matrix of the state variable controller. We can split it into the original matrix Kp that we built when we're building a linear model following system, and the increment. And we put this increment delta Kp, defined as a function of error in time. It is a time-dependent increment of the state variable controller matrix. The same we have for matrix Ku. Matrix Ku, initially fixed matrix Ku, is introduced when we build the linear model following system, and we're adding this increment delta Ku, defined as an error in time. As a matter of fact, it's supposed to have plus here, but it's not that important actually. And this is the control effort applied to the control plant. And we want to split it into two components. First of all, it is U1, the control effort that would be defined within the linear model following system, and U2 and U2 will be the component of the control effort defined by the time dependent components of the control system. So take a look. U1 is defined as state variable controller, negative state variable feedback. Matrix Kp is the matrix of the controller. Matrix Km is the matrix that connects our system to the reference model. X is the state vector of the reference model. Matrix Ku is the one that is placed in the reference channel. And again, matrix Ku here is fixed. This is the one that comes from the linear model following design. But U2 is defined on the basis of the time-dependent increment of matrix Kp and time-dependent increment of matrix Ku. What is the nature of the adaptation that will be performed in our system? The adaptation effectively will be an additional feedback loop that would improve the performance of the original linear system. We will build linear model following system. It will not work perfectly because of the incomplete information of the control plant. So we can add additional feedback loop that would improve the performance, and it will happen gradually. Not immediately, but gradually. This is why the adaptive control effort is a function of time and error. As time goes on, the signal will be changing, taking more and more, taking into account to more and more extent the properties of the unknown control plant. Now, to make our life easy, let's consider signal adaptation. signal adaptation, because technically we can add delta Kp to matrix Kp, and we can add increment delta Ku to matrix Ku, and if we would do it this way, it would be signal adaptation. It would be, parametric adaptation. We would be adjusting matrix Kp and matrix Ku. But we suggest to consider signal adaptation, where the signal will be explicitly generated and applied. The system that we will build is shown in this graph. First of all, I want you to see the controlled plant. For this controlled plant, you see the fundamental matrix AP, you see the matrix BP. The problem is that BP is not exactly known, AP is not exactly known. The next, you see the linear model following design. First of all, we stabilize the control plant by introducing negative state variable feedback with the matrix Kp, and we introduce matrix Km that picks up state vector of the reference model and applies it at this location with plus sign. Obviously, this is the reference model. It represents the design specs. X is the state vector of the reference model. And then, as part of the linear model following design, we have to create matrix Ku, and matrix Ku is the one through which the reference is applied to the input of the control system. Now, if we are lucky, if properties of the control plant are known exactly, then the discrepancy between state vector X and state vector Y, we call this discrepancy the state generalized error. If you follow the books on model reference control, this error is supposed to be 0, and there is nothing to talk about. However, since matrix AP is not exactly known, and matrix BP is not exactly known, then error is not 0. Is not 0. And therefore, this error will be used by the adaptation mechanism. In addition, I have to tell you that the reference signal will be used by the adaptation mechanism, and the state vector of the control plant will be used by the adaptation mechanism. And this adaptation mechanism will create additional adaptation signal U2. And signal U2 will be added to the control effort applied to the control plant. So now, as system is shown here, it has two control efforts. One U1 that is defined within the linear model following system, but since U1 fails, we have additional control signal, U2, that is defined by the adaptation mechanism. And at this point, let's be careful and let's go through the description of our adaptive model following system. First of all, I want you to take a look at the state equation of the control plant with matrix AP, state vector Y, control effort U, and matrix BP. And as I said earlier, AP and BP are not known exactly. Now, we can take this equation and rewrite it by defining signal U. And signal U, matrix BP is exactly where it belongs, and signal U is composed of the state variable feedback with matrix Kp, the state vector of the reference model with matrix Km, and matrix Ku multiplied by the reference. So these are the three components of the control effort U. I have exactly the same expression written right here, and for the sake of algebra, I will add plus bpkm and minus bpkm times y times y. Doing this enables me to obtain the following equation for y dot. For y dot, it is the state equation of the controlled plant with linear model following and adaptive model following mechanisms. Look what you have. This is y dot, which is the derivative of the state vector of the plant. And here in square brackets, I have an expression that I could perceive as some kind of time-dependent fundamental matrix of the closed-loop system, or system with this control effort. And then what you can see is I have something that I can perceive as matrix B. Look, it is BP times KU plus delta KU as a function of error and time. So this could be perceived as matrix B in the state variable, in the state equation of the closed loop system. And in addition, I have BP times Km times error. X minus Y is the state generalized error. And if I would take a look at this expression, I would say that if this expression represents dynamic adjustable system, that all this stuff, all these terms, this one minus this one plus this one plus this time dependent term, they basically define matrix A of the adjustable system, of the parallel adjustable system. And we can define this matrix as function of error and time, but we can also define it as matrix of variable V, intermediate variables, and time. And these intermediate variables, you will see later, they are defined by filtering error vector. And exactly I can show you the matrix B of the adjustable system. This is matrix B of the adjustable system. So in our model reference approach, we have the reference model, and then we have the adjustable system with adjustable parameters. It's a parallel configuration, and in this system, we have matrix B defined as follows. It is function of error and time, but error could be filtered, and by filtering error we will get vector V of intermediate variables. So this is matrix B of the adjustable system. So if this is the case, then the equation for the adjustable system, state equation, will look like this. We have additional term bpkm times error. State variable equation, for the adjustable system looks like this. This is the expression for the error. State generalized error, state vector x minus state vector y. X is the state vector of the reference model. Y is the state vector of the control plant. If I will keep working on this expression, I will obtain state equation for the error in the model reference system. You know, it's our basically approach to model reference control. We're building an equivalent description of the system with linear forward path and nonlinear feedback. And this is the system that could be perceived as the system to control the state generalized error. And this is equation for this system. This is equivalent negative feedback nonlinear system. Error dot eventually is equal to this part times error plus this part times reference and this part times the state vector of the control plant y. I want to write down the expression, or from this expression I will extract the description of the linear time invariant forward path. This is it. This matrix is the fundamental matrix of the error equation. Fundamental matrix of the error equation. And then we have matrix BP times variable W. Now, vector V is filtered error. Filtered error. We have to keep this in mind. And now I want you to take a look at the expression for W. This expression, variable W, converts input signal and the state vector of the plant and implicitly variable V into the input signal of the linear time invariant part. So we can always claim that this expression is the negative feedback that picks up error and effectively converts it into the signal applied to the input of the linear time invariant part. But it is applied through a summing junction with minus, and therefore I can change this expression, and this is exactly the signal that is generated by the nonlinear time varying part on the basis of V, on the basis of Y, and on the basis of reference, and the signal is generated by the nonlinear time varying part. So at this point, we have the equivalent description of the negative feedback system with linear time invariant forward path and nonlinear time varying feedback. And you already know that the linear time invariant part must be strictly positive real, and the nonlinear time varying part must be hyperstable. So it is our responsibility to come up with this law for matrix A of the adjustable system. And for this definition of matrix B of the adjustable system, that would assure the hyperstability of the nonlinear time varying part. And we will start from this. We will start from achieving hyperstability for this nonlinear feedback of the system. How we do it? As always we did it. We have to make sure that matrix function A of the adjustable system, representing the fundamental matrix, and matrix B of the adjustable system have definition that assures some flexibility, because we have to satisfy the Popov integral inequality, if you remember. And this configuration of the matrix A of the adjustable system and matrix B of the adjustable system, the specific configuration that has the integral part and proportional part, the integral part and proportional part, plus initial conditions, this configuration will help us to achieve the hyperstability, providing that we will properly define this matrix function, and this matrix function, and this matrix function, and this matrix function. And this is what we will do. You know, this is definition of the fundamental matrix of the adjustable system. This is the definition. It has parts that are fixed. It has part that is time and error dependent, and it's supposed to be equal to this expression plus initial conditions. And what we want to do is to place these fixed parts into these initial conditions. And what happens here is basically the algebraic expressions that show you how can we define initial conditions for the fundamental matrix. For the fundamental matrix. And if we would come up with the initial conditions for the fundamental matrix properly, then matrix A of the adjustable system will be defined in this form. And after performing some algebraic operations, we will obtain this expression where delta Kp of 0 are initial conditions for the matrix function Kp, and I have Bp right here, and I have Bp matrix on another side of the equal sign, and we can eliminate them, and amigos, we have expression for matrix delta Kp, which is our expression that we will be using for our further exploits. And if we would define matrix B 0, the initial conditions for matrix B in this form, we should be able to get expression for delta Ku defined through the integral part and the proportional part and the initial conditions for matrix Ku. And then, as we spoke earlier, you have to realize that the integral part in the expression for delta Kp and the integral part in the expression for delta Ku is necessary, but the proportional parts are not necessary. It's good to keep this in mind. By the way, delta Kp is supposed to be a function of V and T. Look, it's function of V and T. This is a mistake that I will fix. You will not see this mistake in the hard copy of the file with the text of the lecture. And then, if you would recall earlier material that was presented, this is the way to satisfy the Popov integral inequality. We will define phi 1 matrix function as a function of V and T as some positive definite matrix F times vector V times positive definite matrix G times state vector of the control plane transposed. But if we are willing to make further simplifications, what we will get from this sophisticated expression is this. It will be a positive constant C1 times unit matrix times vector V multiplied by state vector of the control plane transposed. It is a square matrix, by the way. Square matrix. Similarly, the matrix psi that is used to define delta Ku, it is a function, matrix function of V and T. It has positive definite matrix M times vector V times positive definite matrix N times the reference, but this product is transposed. And again, if we are willing to simplify this result, come up with simple expressions for matrix M and matrix N, we will get positive constant C2 times unit matrix times V vector times reference signal transposed. As simple as that. Yeah, this is exactly what I told you. This is exactly what I told you. We using simplified definitions for this positive definite matrices, and we discarding the proportional part. But then we have the second task. We have to make linear time invariant part strictly positive real. What we're supposed to have is the fundamental matrix of the adjustable system transposed times matrix P, which is square matrix, and then plus matrix P times the fundamental matrix. It should be equal to minus Q, where Q is an arbitrary positive definite matrix. And you know, I am suggesting my students to use unity for matrix Q, and this is how you will solve this equation. This equation is known as the Lekanoff equation. This equation is simple if you have 2 by 2 system, second order system. This equation could be very complex if you have a higher dimensional system. However, I recommend everybody to use computer tool to solve the Lekanoff equation. This computer tool is available in MATLAB, in CC, and it is just, you have to use it. Now, I want you to keep in mind, and the following. Let me go back a little bit. Listen, this is how the linear time invariant part was defined. Earlier, when we spoke about the state observers, I had unit matrix here. Here I don't have unit matrix, I have matrix BP, and we have to pay price for this. This means that after I will get solution of the Lekanoff equation, matrix P is not equal to the filter that we use to convert errors into variables V. The filter G is defined as BP transposed times matrix P that comes out of the Lekanoff equation. And I think this is what you have to keep in mind if you're doing not the state observer, if you're doing the model reference control. And then let's summarize everything what we said earlier. I guess the summary is something that should be engraved in your memory at least until you get through the final exam. The summary is this. Number one, you have to get a reasonably accurate best guess description of the control plane, matrix AP and matrix BP. We cannot get the exact definitions, otherwise we would need the adaptive control, but the best guess should be obtained. The next, you have to select the reference model, matrix AM and matrix BM. The reference model must be stable, must be controllable, of course, and must be consistent with design specifications, because our effort will be aimed at making sure that our system, in spite of incomplete information, will eventually behave as the reference model. The next move is to design a state variable controller KP such that the closed-loop system is a Hurwitz matrix. It means the closed-loop system supposed to have all left-hand side eigenvalues. Okay? This act is nothing but the stabilization of the control plant. I don't think we can do more than that at this point. The next, we have to do our best in selecting matrix Km and Ku to satisfy the linear model following equations. We're building the linear model following system. Getting these equations, from the first equation we will get matrix Km, from the second equation we will get matrix Ku. How to get matrix Km and Ku? By inverting matrix BP. If it's not a square matrix, then we have to do the pseudo-inverse. But one way or another, Km and Bm should be defined. They should be defined for a good reason. They may not do a very good job for us. However, they will be included, or should be included, in the initial conditions for the delta Kp and delta Ku later. The next, we have to select matrix P to satisfy the Lekanoff equation. We use computer tool for solving this equation. It's a square matrix. The next, we have to define matrix D, the filter. Why do we need this filter? Because this filter converts vector of errors into vector V. The next I would suggest you to do to obtain matrix phi 1 according to this formula and matrix psi 1 according to this formula. By the way, in this formula I have to have R. Look, I have to have R transposed. Okay, this is something else that I have to fix. This is R transposed. In phi 1 we have Y transposed. Y is the state vector of the control plant. In the matrix psi we have R, the reference signal. This is correct expression. Look, the difference between this expression and this expression is this. Variable V or vector V here is written as vector V, and here I write it explicitly as D times E. Vector V here is written as just vector V. Here it is defined as D times E. Again, this must be R, the reference. The next, what we will do, and again this should be V, not E, expression for delta Kp and expression for delta Ku, and they are defined like this. And later you will see that for initial conditions I use zeros, because we use very powerful techniques, the hyperstability and positivity approach. We're working with the Lekanoff equation. We should get stability regardless of initial conditions. You know, as soon as you use word Lekanoff, we are reaching for global asymptotic stability, and the word global implies that what we will get will work for any initial conditions. And I use zeros. Now, if you would work in industry, if you would try to get the best possible convergence of your procedures, I guess you would use the best available initial conditions for delta Kp0 and delta Ku0. Again, they're supposed to be V, not E. Now, this is what you would do if your goal is to do parametric optimization, because delta Kp should be added to matrix Kp, delta Ku should be added to matrix Ku in the reference channel. This is in state variable feedback, and this is how you would handle the parametric adaptation. Or, if you want to use signal adaptation, then you would define adaptation signal UA. A stands for adaptation, it is function of V and T, and of course it will be delta Kp of V and T, V and T, times Y plus delta Ku of V and T times R. And this is the end of the story, because the next what I want to do is to offer you concluding remarks and get into a case study. I will discuss with you every single aspect of implementing everything what we have been talking about. Concluding remarks. First of all, adaptive model following control system is an extension of a linear model following control system. And this extension is required when parameters of the control plant are not exactly known or poorly known, or parameters of the control plant may vary during the operation of the system. Number two, adaptive model following control system can be formulated as model reference adaptive system design utilizing conditions for the perfect asymptotic adaptation. Do you remember what perfect asymptotic adaptation is? Perfect asymptotic adaptation is the situation when you get equivalent equation for the error when you're getting the equivalent negative feedback system for error, the negative feedback system with linear time invariant forward path and nonlinear time varying feedback, and this nonlinear system is globally asymptotically stable. So if equivalent negative feedback system is globally asymptotically stable, then the model reference adaptive system has perfect asymptotic adaptation, which means that it will work for any feasible parameters of the control plant. Number three, if necessary, the adaptive model following system, as we presented it here, could include special design of an adaptive model following state observer if necessary. I do not want to create this monstrosity, but keep in mind, building adaptive model following system does not imply that you cannot use the state observer, adaptive state observer in the system. The next issue is this: the integral adaptation law is sufficient. However, adding proportional part would improve the convergence. I also want to add that when you solve the Lekanoff equation, in the right-hand side you have a positive definite matrix Q. It is an arbitrary matrix, but this matrix could be chosen more successfully or less successfully, and this will affect the convergence rate of your adaptation adaptive control mechanism. It was stated earlier that adaptive model following control presents an approach for the rejection of external disturbance signal because the model reference system, technically, it is a subroutine in the flight control computer, let's say, and weather conditions, flight conditions cannot affect dynamics of the reference model. But the real control system is affected by disturbances. However, when we're building the adaptive model following system, we're creating conditions that would force real control system to follow the reference model. By doing so, we can reject external disturbances. Now, I also want to tell you that the feasibility of the design control system is limited by the magnitude of the control effort. I want you to realize that when you apply control efforts in the simulator, in the electronic environment of your flight control computer, there is no limitations on the magnitude control effort. Effectively, you can force airframe of B-52 to have dynamics of a tiny aircraft, of a quadcopter, on paper in the simulation. But when it comes to the realities of life, the magnitudes of the control efforts are limited, and therefore don't be too optimistic about the ability to completely modify dynamics of the control plant. What I want to add is this. There are situations when, because of the controllability problem, you cannot build a linear model following system. It has something to do with the dimensions and ranks of the particular matrices. Matrix AP, matrix BP, matrix A of the reference, matrix B of the reference model. There are situations when building a linear model following system is not a done deal. And because of this, if you will not be able, due to the dimensions, due to the properties of particular matrices, build a linear model following system, keep in mind that adaptive model following system also will not be successfully built. This is something that you should keep in mind. And I faced it by preparing exercises for my students. Several times I was not able to make linear model following system work. And I was really surprised. But then I checked the dimensions and properties of the matrices, and I realized it cannot be done. It cannot be done. We're ending up creating a uncontrollable system. After saying all this stuff, I want to get with you into a case study. I will be working with you on a very particular expression for the control plant, expression for the reference model, and we will perform every single step in the way of building a successful adaptive model following system. Let me start from the definition of a reasonably simple controlled plant. This is the state equation of the control plant. I have matrix AP and matrix BP, but I want to emphasize that they are best guess matrix AP and best guess matrix BP, because with this matrix AP and BP, I will be able to build a very successful linear model following system. But when I will apply linear model following design to the true control plant, I will immediately realize that adaptive model following system should be built. Therefore, I introduced the true description of the control plant, and I want you to see that the elements of the matrix AP are different, not drastically, but quite different, and elements of matrix BP are different. So the true description is not equivalent to the best guess description. However, the true plant is supposed to be unknown to you and me, and therefore linear model following design could be based only on the best guess description. After I got this best guess description of the control plant, I checked the eigenvalues of matrix AP, best guess, and I found that they are equal to 3, plus 3, and plus 4, which means that the, according to best guess, control plant is unstable. My first task is to stabilize the control plant. I want you to take a look at the control plant. It looks like it is a system with two state variables and two inputs. It's a two-input. You can view it as a two-input, two-output system. Obviously, in reality, one of the state variables could be designated as the output, or some kind of combination of two state variables could be defined as the output, but it's not necessary. It's not critical for our design. At this point, I view our control plant as a plant with two input signals. How to stabilize the control plant, and I stand for the simplest possible solutions. I want the stabilized control plant, or I want to introduce a state variable feedback controller that would give me closed loop poles of the closed loop system equal to -1 and -4. If this is the case, the simplest way to introduce the desired closed loop matrix A is as a diagonal matrix. Nobody would argue with me now. In the matrix A closed loop, that will be desired closed loop fundamental matrix, I have two left-hand side eigenvalues, -1 and -4. But this A closed loop supposed to be equal to matrix A of the plant minus BPKP, where KP is the state variable controller matrix, and AP is the matrix of the control plant. And from this expression, without any unnecessary headaches, I am getting definition of matrix KP. It is BP in the power of -1, AP minus A closed loop. And this is the definition of the state variable controller matrix KP. Technically, when you do this type of design, I would suggest once you get the closed loop transfer function, now you have AP, you have BP, you just got KP, can you just get the closed loop system and check its eigenvalues? And I would tell you that eigenvalues are exactly what you wanted them to be. I just did not put this check in on this page. Now I want to take a look at the system design specifications or system dynamic requirements, and I want to engrave them into the reference model. The reference model is x dot is equal to AMX plus BMR. First of all, R is the reference. Therefore, you have to realize that the reference model is the desired closed-loop system performance. Now, matrix AM is a diagonal matrix, and it has two eigenvalues, -6 and -8. Matrix BM is also a diagonal matrix, and on its diagonal I have 6 and 8. You know what this means? Since both matrices are diagonal, you have to realize that this description with these two matrices, AM and BM, represent a fully decoupled system with two first-order channels. And for each of these channels, I can get transfer functions, G11 and G22. And the system is decoupled. So not only I am forcing the required dynamics through the reference model. Through the reference model, I will try to enforce the decoupled property of the resultant system. And we will get engaged in the linear model following design now. You know, in the linear model following design, there are two equations that we have to satisfy. The first equation is BPKM is equal to this expression, where Km, the matrix through which reference model, state vector of the reference model, is included in the operation of the control plane. I have matrix BP. Matrix BP is a square matrix. I have no problem inverting it, and therefore I'm getting matrix Km from this expression without any problem. And this is matrix Km. Don't be surprised. It is a system with two inputs and two outputs. And because of this, matrix Km is a square matrix 2 by 2. Through matrix Km, state vector of the reference model reaches the control plane. Now, the second equation of the linear model following design is this. BPKU is equal to BM. And again, since matrix BP is a square matrix, it is very easy for me to define matrix Ku. And don't be surprised again, it's a 2 by 2 matrix because the system has two reference inputs. It's a system with two inputs. It is the system that's supposed to behave as two independent first-order systems. So I have matrix Ku now. And the best what I will do at this point, I will check my results by making sure that I obtained a fully operational linear model following system. First of all, I want you to see the reference model. This is the first equation of the reference model. Two inputs R1 and R2, two state variables. This is the second state equation of the reference model. Again, two state variables. This is x2 and two input, two reference, R1 and R2. Well, I guess these two elements are first row of matrix A model. These two elements are second row of matrix A model. These elements are first row of matrix B model and second row of matrix B model. So no problem with the reference model. The next what you have is the best guess description of the control plant. Best guess description, because we built linear model following design for the best guess description. Again, for the plant, we have state variables y1 and y2. These are two elements of the first row of matrix A, two elements of the first row of matrix B of the plant, two elements of the second row of matrix AP, and two elements of the second row of matrix BP. And we have two control efforts, U1 and U2, U1 and U2. Now, don't be confused. U1 and U2 we have because it is a controlled plant with two inputs. So the control effort per se has two inputs. It has nothing to do with the adaptation signal. Don't be confused about this. The control plant has two inputs. What you can see here is the linear model following circuitry. Look, this is x1 and x2, state variables of the reference model applied through elements of the first row of matrix Km. Here, x1 and x2, state variables of the reference model applied through two elements of the second row of matrix Km. Here we have the state variable feedback. Y1 and Y2 state variables of the control plant are applied through two elements of the first row of matrix Kp. Y1 and Y2 are applied through two elements of the second row of the matrix Kp. And finally, R1 and R2 applied through the two elements of the first row of matrix Ku, and here they apply through the elements of the second row of matrix Ku. What do we have as a result? As a result, we have U1 right here and U2 right here. And here, I'm testing my system. The system is supposed to behave as a decoupled system. So look what I do. I am applying step input to the input number 1 of the reference model, but it's also applied to the control plant, of course, through linear model following circuitry. And look at this. Here I have state variable x1 of the reference model and state variable y1 of the control plant, and there is no difference between them. Now, this looks different. I have here second state variable of the reference model and second state variable of the control plant. For the reference model, I have 0 clearly, but for the control plant, I have something in the power of -17 that is 0 for all practical purposes. Here I reverse the situation. I am applying step to the second input of the reference model, and of course through the circuitry it is applied to the control plant as well. For the first two state variables, I effectively have zeros. Clean 0 for the reference model and something in the power of -16 for the control plant. But two other variables coincide completely, and we have what was expected to have. This is basically step response of the second independent channel of the reference model. It looks great, but why it looks so great? It looks so great because It was designed for the best guess, and it was tested on the best guess. And we don't have the best guess, we have the true system. And when it comes to the true system, and the true system was, look, this is the true plant, and this is the true plant. When it is applied to the true plant, you can see that there is no decoupled performance for the controlled plant. There is no match between the state variables of the controlled plant and the reference model. It doesn't work for the controlled plant. Why? Because system was designed, linear model following system was designed for the best guess and applied to the true controlled plant. The discrepancy between properties, between state variables of the reference model and the control plant indicates that we have input information for the adaptation mechanism. And here I engage in the adaptive model following design. First of all, I solve the Lekanoff equation and I obtain matrix P. The solution of Lekanoff equation is always a square symmetric matrix. And it is square and symmetric, all right. It's also diagonal matrix. That makes our life easy. And then I define matrix D, the filter that we will use to convert state vector, vector of errors into vector V. Honest multiplication of BP transpose by P gives me this result. And of course I use software tool for all these computations. Now I want you to see the definition of vector V. It is 2 by 1 vector. This is D times vector E1, E2, and I am getting a 2 by 1. And this is the definition of V1, and this is the definition of V2. Later, I will be using these definitions in my work. Let's take a look how matrix function phi1 looks. First of all, it is a positive constant. Then I used to have unit matrix, but I don't need it. Actually, I have vector V times Y transpose. And matrix function phi1 is a 2 by 2 matrix, and this is how individual elements are defined. V1, Y1, V1, Y2, V2, Y1, V2, Y2, and each of them should be multiplied by positive constant C. So correspondingly, this is phi11 equal to V1, Y1, and so on. Similarly, I obtained the matrix function psi1 as a constant, vector V times reference transpose. And I have this definition for each of these variables, components of the matrix phi1. But what we have to do now, we have to take integral of phi1 and integral of psi1. Now, which means that I have to come up with independent integrals of phi11. Independently, I have to integrate phi12, phi21, and phi22, because matrix integration is not available to me. Similarly, I have to independently integrate psi11, psi12, psi21, and psi22. And here what I wrote. element data delta kp, element ij, will be defined by this integral plus initial conditions. Individual element of matrix Ku, element ij, will be defined by this integral plus initial conditions. And as a matter of fact, since we have the property of perfect asymptotic adaptation engraved into our system through the Lekanoff equation and hyperstability and all this good stuff, I will use 0 for initial conditions, because I want you to show that system works. If I would be working for a customer, I would try to make performance as glorious as possible, and of course then I would pay attention to initial conditions. Now my goal is to get the adaptation signal. This adaptation signal has two components, UA1 and UA2, and it is, look, UA1 is defined as this row, delta KP11, delta KP12 times Y1, Y2, plus delta KU11, delta KU12 times R1, R2. The second component, UA2, will be defined as this row times this column plus this row times this column. And I still have to inject these two components of the adaptation signal into the linear model following circuitry. Yeah, this is the continuation of this definition of U1. This plus this is U1, UA1, and this plus this is UA2. The next is the block in my simulation that defines errors. Look, I have x1 minus y1 is error 1, x2 minus y2 is error 2. And then I have error 1, error 2 multiplied by the first row of matrix D, which was earlier defined. And I getting V1. And I have error 1, error 2 multiplied by the second row of the matrix D, and I'm getting V2. The next, what you should see, the definition of the individual elements of matrix function phi 1. This is phi 1, 1, phi 1, 2, phi 1, 2, and phi 2, 2. And here I use 10 for the constant gain. Later I change this value. Okay? Well, phi 1, 1 is equal to V1 times Y1. No problem. Look. Phi 2, 2 is equal to V2 times Y2 times the constant gain. And the value is defined right here. So everything is done properly. The next, what you see is definition of the individual components of the matrix function psi 1. I have constant gain. Later I change the value of constant gain. Look, psi 1, 1 is equal to V1 times R1. Look, psi 2, 1 is equal to constant. This is the value of the constant. V2 times R1. Everything is done right. But then I have to integrate psi 1, 1, psi 1, 2, psi 2, 1, psi 2, 2, and I have to integrate phi 1, 1 and phi 1, 2, and I will get elements of matrix K or matrix delta KP. Look, here you have elements delta KP. I have element delta K 1, 1. It is equal to phi 1, 1. integrated plus initial conditions. And you see clearly I use 0 for initial conditions. Look, delta K, P, element 2, 1. It has phi to 1, integrated plus initial conditions. Everything is done right. Similarly, I define individual elements of matrix delta KU. Look, element delta KU 1, 1 is psi 1, 1 integrated plus initial conditions that I again use zeros. Look at this one. Delta KU 1, 2 is equal to psi 1, 2 integrated plus initial conditions. I think it is done properly. I'm sorry I have cold, but at least through camera I cannot infect you. Look at this. This is the generation of the adaptation signal. This is how I build the adaptation signal. Look what I have. I have delta K11 times Y1 plus delta K12 times Y2. I have delta K11 times R1. I probably, yeah, then this is basically correct. So look what this is. This is the part of the state variable feedback, because elements of the state variables of the control plant I multiply by the elements of the first row of matrix KP. It's perfect. Here I have elements, state variables of the controlled plant multiplied by the elements of the second row of matrix KP, state variable feedback. What do we have here is this. I have elements of the first row of matrix delta KU. This is delta KU11. This is element of the first row, second element, delta KU12, multiplied correspondingly by R1 and R2. They are components of the reference. So by doing this, I'm getting the first component of the adaptation control effort. And by doing this computation, I'm getting the second component of the adaptation control effort. What's next? And the next you will see, you saw this earlier. This was the linear model following circuitry. But in the linear model following circuitry, I am adding U adaptation 1 and U adaptation 2. So this is U1 and U2 control effort applied to the plant, and I am adding additional adaptation signal. First component of this adaptation signal and second component of the adaptation signal. The first, what I did when this is done, I want you to see the result with the disabled adaptation mechanism. You can see that I'm applying sinusoidal signal to the input of the reference model. What you will see in the output, no convergence. Actually, there is even divergence. There is a stable discrepancy that does not diminish with time between the reference model and the control plant state variables. Here, this is 0 for the reference model, second state variable, and for the control plant I have something with the magnitude of 0.04. Okay, now to follow this logic, I was supposed to apply the sinusoidal signal to the second input, but I just decided to save paper. And moreover, later I will show you that with the step input, I'm getting much better result, much more educational results. Okay? what you should see now is that adaptation mechanism is enabled. I'm applying sinusoid to the first input of the reference model. I see absolutely no difference between the state vector of the adjustable system and state vector of the reference model. They fully coincide. Here you can see converging effect of the input on the second channel, the channel that's supposed to have no response in it. But the magnitude is something in the power of -6, and it converges to 0. So our decoupling does work. This is the result when you see when I applied sinusoid to the second input of the reference model. The first outputs or first state variables for the reference model, it is 0. For the control plan state variable has magnitude of 0.00015, for example, and it converges with time. For the second state variable, there is virtually no difference between the state variables. And even better results I have for applied step input to the first input of the reference model. Look, I have perfect change of these both state variables of the reference model and the control plant. Okay, this is the expected response of the fully decoupled system. Okay, now for the second output, I have very small magnitudes, and the result converges quite successfully. So the coupling does work. However, when I applied step to the second input of the reference model, for second state variables, you can see perfect response as it's supposed to take place, and the first state variable of the reference model is 0, and state variable of the control plant converges to 0. The magnitudes are very small. So at this point, I want to report that the technology presented in my class does work, and it is just a matter of time before you will be able to applying this technology. I think it will become part of your final exam, or the final take-home exam. Now, what is happening now, at some point, you will be getting your test number 1, which will be in class, and I will give you 2 hours for this test. And for the test, you have to be prepared. So next time, next lecture, will show you another case study, more complex, and you will have some problems to take a look, because it will be type of problems that you will face during the first in-class test. So thank you very much.